Welcome back, folks. Today we will be talking about section 10.4, Trigonometric Identities. And just to give you a little heads up here, this lesson is going to be divided into several videos. The first video will be kind of a little bit of notes, and then the rest of the videos will be a lot of examples. And what I will do in those examples is kind of try and show you a correlation between the example problem I'm showing you and what you're going to find in WebAssign. But first, let's get down to some of the background information that we need to be successful in this section. So first, question for you. Do you remember what makes a function odd or even? Well, I do, and it's the following. If f of the opposite of x equals f of x, then the function f is even. And that is illustrated by our friend y equals x squared, which is an even function. That is the classic textbook example of an even function. Okay, so what about this other example here? If f of the opposite of x equals the opposite of f of x, then the function f is what we call odd. And our textbook example of an odd function is y equals x cubed. Okay, so why review those things here when we're talking about trig? Well, as it just turns out, some of these this idea of even and odd have an application with respect to trig, and we're going to get into that now. Okay, so the next example here says if we know theta, what can we say about the opposite of theta? And the note here is I'm going to use two different colors to kind of do this one, and I would suggest you do the same. So the first thing I'll do is I will graph theta in red, and then I'll graph the opposite of theta in blue, and if you're colorblind, I apologize. All right, so let's take a look at theta. Theta is pi over 3, and because I've done a good job so far this semester of memorizing the unit circle, I remember that that's this angle right here. So that's theta. So now let's talk about the opposite of that. Well, the opposite of that would be negative pi over 3, and that would just go counterclockwise, so it would have a initial side right here in standard position, and then going counterclockwise. That's the opposite of theta. Okay, let's go ahead now and look at the next example here, negative 3 pi over 4. So negative 3 pi over 4, my initial side here is in standard position, and I have, this would be negative 1, 2, 3. That's negative 3 pi over 4 right there. And the opposite of that would be positive 3 pi over 4. Well, that's an easy one. Initial side, terminal side, that's the opposite of theta. Okay, so I'm starting to kind of see a pattern here. Let's do these last two examples and see if that pattern emerges any more clearly. So theta in this third example is negative 7 pi over 6. So I have my initial side there in standard position, and negative 7 pi over 6, that's going to be 1, 2, 3, 4, 5. So negative 7 pi over 6 shows up there. And that angle right there is theta. And that theta is measured this way. Okay, now let's take a look at the opposite of theta. So the opposite of theta is going to be 7 pi over 6, and that's, I certainly remember how to do that. That's 1, 2, 3, 4, 5, 6. So that's right here. Now, it's starting to get some overlap here. Hopefully this isn't too confusing, but that guy right there in blue represents the opposite of theta. Okay, definitely seeing a pattern emerge here. Let's take a look at this last one and see if the pattern holds. So if theta equals pi, that's real easy. That's this angle right here. The initial and terminal side lie right on the x-axis, and that's theta. Now let's take a look at negative theta. Well, that's just going to be negative pi, which is that angle right there. So I'm pretty sure I have a clear conjecture here. It appears that the opposite of theta is a reflection of theta across the x-axis. And that idea is going to become really important here as we look at the even and odd identities, the even and odd trig identities. So now let's talk a little bit about even and odd identities, even and odd trig identities. I want to kind of highlight one thing here. If I look at what we did in the previous examples, I notice this. When theta is reflected across the x-axis, this line right there indicates that, hey, look, the x-coordinates don't change. So if I reflect a point across the x-axis, the x-coordinate does not change. But when I reflect a point across the x-axis, the y-coordinate does change. If the y-coordinate was positive, it becomes negative. If the y-coordinate was negative, it becomes positive. So this line right here, I'm just kind of showing you, if you reflect across the x-axis, the y-coordinate changes, the x-coordinate does not. That's going to give us some insight as we begin to talk about even and odd identities here. So the cosine of the opposite of theta, well, I know that the x-coordinate doesn't change when I flip across the x-axis. So that means the cosine of negative theta is just the cosine of theta. And let's take a look now at the secant of the opposite of theta. Well, secant is 1 over cosine. So because the x-coordinate is not changing, the secant won't change either. And for both of these, I just want to make the quick comment that the reason that these two identities equal the trig function of the original is because the x-coordinate doesn't change. Okay, so let's take a look at the rest of these. So we'll talk now about the sine of the opposite of theta. Well, remember what we showed in this picture up here. So for the sine of the opposite of theta, the y-coordinate does change for that because it flips across the x-axis. So the sine of the opposite of theta is equal to the opposite of the sine of theta. And that relationship is going to hold for the rest of these trig functions. Same is true for cosecant, tangent, and cotangent. And here the reason for all 4 of these changing the way they do is because the y-coordinate does change. So what I'd like to do now is kind of give you a little challenge. Back at the top of the page, we talked about even and odd functions, and the challenge question for you is which of these 6 trig functions is even and which is odd? And you should be able to kind of look at what we've done and figure that out after a little bit of thought there. All right, let's move on to the really the big deal in this lesson. We're going to start to get into some really crazy formulas, and the first of those is the sum and different identities for all angles alpha and beta. So the sum and different identities, they're here for you. They're typed out for you on your notes page, and I'm just going to tell you the following. If I put let's go with a fancy color. Let's go with purple. If I put a purple star next to a formula, that's one you have to memorize. Memorize these. Okay. So you'll notice that I've put a purple star next to, or purple asterisk next to cosine of alpha plus or minus beta and sine of alpha plus or minus beta. I guess what I should go back up and do here is these even odd identities. You got to memorize those as well. I did not put a purple asterisk next to tangent because that's one I'll provide for you on any test we take. But these sum difference formulas, there's a couple things worth highlighting here. Alpha and beta are 2 angles, and we can add 2 angles on a graph just by making the terminal side of one angle match the initial side of another, and then we get a bigger angle based on the sum of the two. So you'll notice that that angle alpha shows up here and here, and then the angle beta shows up here, here, and here. And the thing that's worth noting for this sum difference of cosine is here, the plus sign's on the top. That matches up with a minus sign here. For the sine of alpha plus or minus beta, if I have a plus sign there, I have a plus sign there. Okay, so that's sometimes tricky for students, and that'll make more sense as I get into actually showing you an example or two in the next couple videos. All right, let's move on to one more pair of identities here. These are the cofunction identities, and I'm going to go ahead and I'm going to just grip it and rip it through these, and then we'll explain. All right, folks, there's your cofunction identities, and there's a little question here that says, what do you think the co might mean in cofunction? Well, let's take a look at some things. I'll highlight some things here. I got this angle here, theta over, or excuse me, pi over 2 minus theta, and then theta. And let's talk about that. What's the relationship between pi over 2 minus theta and theta? What is the relationship there? Well, the relationship is, this might be easier if we thought of it like this. Let's add these two and see what you get. Pi over 2 minus theta plus theta, well, that equals pi over 2. Okay, and if I have two angles that add up to pi over 2, don't forget that's 90 degrees. If I have two angles that add up to 90 degrees, we call those angles complementary. So that means pi over 2 minus theta and theta are complements. And in a geometric sense, that means those two angles add up to 90, or pi over 2, if pi over 2 radians. So where does the co come from in cofunction identities? It comes from the fact that pi over 2 minus theta and theta are complements. All right, folks, that's it for page 1. Let's take a quick look at page 2. Page 2, there's not going to be a lot of discussion, just kind of me pointing to some formulas, telling you which ones you have to memorize, and then eventually we'll get to some examples. By the way, cofunction identities, yeah, you got to memorize those. So far on this page 1 of the notes, we've got the even-odd identities you have to memorize, cofunction identities you have to memorize, and then the sum difference formula for cosine and sine. All right, page 2. We've got a whole bunch of formulas here. Again, don't mean a whole lot till we start doing some examples. I will tell you this. Memorize. Memorize. Power reduction angles. Power reduction formulas for all angles theta. We don't have to memorize these two. Don't have to memorize those two. So we'll continue to move on down. Half angle formulas. Yeah, take a look at these half angle formulas. We've got we've got 3 different ones. I'm not going to make you memorize any of those. I'll give you any of those that you would need on a test, but these are worth talking about because right here there's a plus or minus here. That means I have to make a choice, and it says the choice of plus or minus depends on which quadrant the terminal side of theta over 2 lies. Okay, so I'm just going to make a couple notes here about that. If theta is in quadrant 4, comma, where do you think theta over 2 is? Well, theta over 2 is in quadrant 2. So let me just show you my thought process on here, and then I'll let you work out the other quadrants on your own. So I know this. Quadrant 4 means that theta is between 2 pi and 3 pi over 2. Okay, that's the range of angles for quadrant 4. Well, if I want to know where theta over 2 is, that means I need to, if I divide that by 2, I have to divide that by 2, and I have to divide that by 2. So that tells me, let's see, I'm going to have 3 pi over 4 is less than theta over 2, which is less than pi. And that clearly is in quadrant 2. So that's kind of the thought process that I go through when thinking about which angle is the terminal side of theta over 2 in, as I picture, well, what quadrant is theta in, and then I divide that quadrant in half to see where the result lies. You can do the same thing for quadrant 3, quadrant 2, and quadrant 1 to figure out where those results lie. Okay, a couple more angles, a couple more trig identities here. We have product to sum and then sum to product. And the thing I'd like to highlight here is product to sum means I'm changing a product. You'll notice on the left-hand side here it's all multiplication. So we're changing a product to a sum. And this is not a set of formulas you have to memorize. These will be given to you on the test if we need to use them. But it's doing exactly what it says it is. We're changing a product of two numbers to a sum or difference of two numbers. The sum to product formulas do the opposite. Sum to product formulas take a sum or difference and turn it into a product. All right, folks, that's a brief introduction to all of the trig identities we're going to be working with in section 10.4. The next part, which is really the harder part, is actually applying these things to some problems. So stay tuned for that in the next couple videos.